years ago, a little over 10 years ago, people got together, mostly from the Department of Energy, and said, if we're going to build exascale systems, what are the big challenges? And one of the ones that a lot of people focused on was, how are we going to power the thing, right? And so, in fact, part of that, they did kind of what I think is kind of a silly little exercise, in that they said, current systems are 20 petaflop systems. If we take 50 times that, we could deploy a exascale system today, and that requires this much power, and so that would require half of a gigawatt of power, and so that would be like kind of unaffordable. And so they're like, so this is obviously a huge problem. And then they arbitrarily said that when we get to having exascale systems, it can't require more than 20 megawatts. And I don't know how they pulled out that number and where they got it from, but they did. Anyway, so kind of looking at and giving a perspective on how have we done on the power question, I went and I looked at the Green 500, which was put together by some people I've worked with over the years. Wu Feng and Kirk Cameron were the main ones who started it. And it basically started in June of 2013. So you've probably seen Eric Strohmeyer does this top 500 slide where he says, here's the cumulative performance of the top 500, here's the performance of the number one system on the top 500, and here's the performance of the number 500 system. And it gives you kind of a bound of where things are over time and how they go up. So I thought I would do that with the Green 500, at which point I learned a few things about the Green 500, which is, first of all, until very recently, they didn't consistently have 500 systems on the Green 500, so I don't know. And so, like looking at that, like taking the cumulative, well, that doesn't really make a whole lot of sense. And taking the 500 system really didn't make any sense, because there would be places where it would be zero. So instead, I just graphed the number one system, and it has some oddities like this dip here. So typically on the top 500, the number one system doesn't go away until there's a new number one system. I guess I don't know what happened there that we get that dip, but apparently whoever had the number one system didn't submit it again. That's all I can conclude from that. But nonetheless, we see a pretty steady progression over time, over the last 10 years from in energy efficiency. So this shows gigaflops per watt. This is as measured by running high performance LINPACK or HPL on a given system and measuring how much energy it uses to perform that computation. And so, it was down around roughly 3 gigaflops per watt. And then on the last list, it was over 65 gigaflops per watt. So that's pretty good. This system here is the test and development system from Frontier, Frontier was the first exascale system. The test and development system is kind of a staging system for that machine. So it doesn't have as big a network or as many nodes. So basically it's able to run LINPACK a little bit more energy efficiently than Frontier was. So Frontier on that list was number 2. Now those systems are like 3 and 5 or something like that. I don't remember exactly. Anyway, so in looking at this, the question, it raises a number of questions. And so the first thing we want to think about is, what can we do to improve energy efficiency? I've done a lot of research. I mentioned some of the people I've worked with over time. I worked with Mark on some things like looking at energy efficiency. And a lot of that work is really focused on software techniques. All right. And so like we've done things like saying, well, I'm running a big MPI job on a system. What can I do to make it so it uses less energy, but still gets done in the same amount of time. And so that ends up looking at things like, oh, we have some load imbalance. If I slow down the MPI processes that have less work, I can still get the job done in the same amount of time and just reduce the amount of energy. So we've used things like dynamic voltage and frequency scaling to do that in research. So it's been pretty good research. There's been a lot of good papers published on that. So then the next question is, well, so what has led to the improvements historically? If we actually had 30 years of data, we would see a pretty continuous trend, even back before, even though this starts here. If we put it into megaflops per watt, you could keep going back down. So one could ask, oh, so this academic research has had a lot of impact, and the answer is no. In fact, not for the most part. Nobody actually uses those techniques in production, largely because they require things like allowing arbitrary users to change the frequency of the processors in your system. And well, we don't trust average users to do that. So no, we don't actually let that happen. Instead, the improvements have largely been through improvements to the way the hardware works. All right. So most recent hardware, you have a lot of things that basically come under the heading of clock gating. So different parts of the processor, if they're not being used, or if they're being used relatively, the utilization is relatively low, then they'll clock down, and you'll change the total amount of power that they're using. So that's led to great improvements in energy efficiency when we're running our actual codes. The other thing that it's led to, which is somewhat of a surprising and creates other problems, is that how much energy does your system use when it's on but nothing's running on it? All right, what's the idle power? And it turns out that the gap between idle power and power used when you're actually running stuff you care about has narrowed substantially over the last 10, 20 years. But anyway, so as I said, the main way we've improved energy efficiency is by making the hardware more efficient. All right, and so we can ask, well, will these historic improvements continue? And yes, probably for a while at least, but a lot of those improvements come out of, some of them are being more clever. Like I said, turning off parts of the chip that you're not using. But a lot of them are just by having process technology that it has smaller transistors. You basically get improved energy efficiency out of that. As you'll hear, we'll be using 5 nanometer process-based chips in El Capitan. Frontier uses 7 nanometer. Where does it end? Nobody can be certain, but I think everybody agrees that we're kind of coming to the end of that change. I've recently seen some stories about 0.5 nanometer and 0.3 nanometer stuff being run in the labs. By the time you get to 0.3 nanometers, there's not really a lot of atoms left. So that's pretty much probably the end of it. So generally, I think people are thinking, maybe there's 4, 5, 6 more generations of process shrink, and then we're at the end of that. So that's a concern as we think about the future and how do we make systems more energy efficient. Perhaps it's an indication that some of that academic research will have impact in production. Another question that I want to revisit as later in the talk is, how should we actually measure energy efficiency? I said that the Green 500 uses gigaflops per watt based on HPL. Is that a good metric? Well, what if I'm not running work that looks like HPL? All right. Well, in particular, like people who are thinking about building AI systems are now talking about ML performance per watt, right? There's a variety of metrics you can use, But the real question to ask to me is what are the shortcomings, and does it really measure what you're doing with the system and why you're running it well? And there's a question about that I'll come back to later. And then some other things to think about is, do users actually care about whether your system is running, if it's being run with good energy efficiency? What determines how effective in production your system is in terms of energy efficiency is what the users run. And, largely, we can do some things to help improve it automatically, but largely it's up to the users whether or not it is efficient. So typically the centers like Livermore Computing, we do want to cut down our power bills, but is that really the number one reason we're building these machines? And the answer is no. And then ultimately, the other question is, if we improve energy efficiency, what are its implications? All right. And does that answer the concerns people have when they start asking about how energy efficient is how efficiently are you using the energy going into these big systems? Do they really care that I'm using the energy efficiently, or is it there's something else motivating it, like climate change? And I think it's really the latter that's what they're concerned about. And so does that actually address it? And I'll answer that later. All right. So enough about energy efficiency for now. I'll finish up by coming back to that topic. But for now, I'm going to tell you about El Capitan. And to understand El Capitan and what we use it for and why we're building it, you have to realize that so Lawrence Livermore National Lab is a National Nuclear Security Administration laboratory. That means that our primary mission is stockpile stewardship. So yes, nuclear weapons. And so basically ensuring that the U.S. Stockpile is safe and secure. The systems we build kind of fall into three different categories. So in the NNSA, the program that builds our big computers is the Advanced Simulation and Computing Program. So that's who pays most of my salary. And that came from the Advanced Strategic Computing Initiative, which was started about 28 years ago, shortly before I started working at Livermore. And so that was started because at the time they were putting together the Nuclear Test Ban Treaty. And the question was, how can we know that the weapons that we have are going to function as intended if we should need to use them, or even more importantly, won't go off when we don't intend them to go off, when they're just sitting in the silos and in the subs and such, if we're not actually able to test them and see how they're doing. All right. And so the answer was, well, we'll simulate things, and we'll build really big computers, and that will help us understand how things are aging. All right. So that was the beginning of the ASCII program, and now we continue following in that mission. So anyway, so we build systems in kind of two main categories. I won't really talk about this third one, which is really experimental systems that get housed at Sandia. But they come under two main categories: commodity technology systems and advanced technology systems. Commodity technology systems are they're the evolution of a line that was at one point called the Tri-Lab capacity clusters. All right, and so these are basically big Linux clusters. Most of them use Intel CPUs, and we do have some with GPUs. We have some with AMD processors. We even have one or two with ARM-based processors. But largely they're pretty much standard Linux clusters. We run something we call TOS, the Tri-Lab operating system software on it. We do a lot of the integration ourselves on those. But the idea is that basically these run kind of smaller jobs and they're smaller systems. And then the advanced technology systems are kind of our cutting edge technology and our biggest systems that we build. All right. And these go back many years. Again, it's evolved from previous systems. When I started at Livermore, we were citing a system called Blue Pacific. At some point, we called those systems the capability systems. You know, the names evolved over time, but currently at Livermore, our largest system is Sierra, which was ATS2. All right, and that's a IBM-based system with Power 9 processors and NVIDIA Volta processors. The last time I was here, I talked about it. So I won't go into it too much. It's currently the number 6 system on the top 500. It was at its peak, it was the number 2 system. Anyhow, it's now just about 5 years since we accepted that system. So in terms of supercomputer age, that's getting pretty old. It gets pretty hard to get replacement parts after a certain period of time. So we're actively working to replace it, and within about a year we'll be retiring that system, and then we'll replace it with El Capitan, which will be ATS4. So I'll tell you a lot more about El Capitan, but first let me say I think something people often don't realize is that building and running a very large scale system involves a lot more than just the computer hardware itself. And so I mentioned that there was this kind of arbitrary 20 megawatts is how much power we need for a exascale system. And I don't know where they came up with that, but at our site, we've recently completed this Exascale computing facility modernization project in order to be ready to house El Capitan. All right. And so I mentioned that we currently have Sierra running, and we're actually in the process of starting to site El Capitan. Our strategy is regularly to be running the existing system while we bring up and accept and bring into production the new system. So at transition time, we're running actually the 2 biggest systems at the same time. All right. And that's important because our mission doesn't go away just because we're getting a new computer. So we really need to be able to do that. And that kind of has implications for what our facility needs to be like. I'll show you kind of a picture in a little bit, but we basically have 2 side-by-side fairly large computer rooms. And over time, that facility has grown from originally 3.5 megawatts, quickly went up to 7 megawatts, 15 megawatts, and 30. When we sited Sierra shortly before that, we took it up to a 45 megawatt compute facility. And looking at what we would need going into the future, we house many other systems besides Sierra there already. We have 3 data centers essentially at Livermore. Building 453 is far and away the largest of them, but we run over 40 clusters. So I mentioned the CTS systems. We have several CTS systems, many other types of systems as well. So we need a lot of power. Anyway, so the ECFM is how we took our facility and made it ready to do that. The split here is a little unfortunate. This says we upgraded the electrical supply to the facility from 45 megawatts to 85 megawatts. All right. And that's actually the power that goes to the compute floor. All right. So that's 85 megawatts that we could deliver to systems on our 2 compute floors in building 453. We also upgraded the cooling to 28,000 tons from the existing 10,000 tons. All right, so we almost tripled the cooling. And in fact, the cooling accounts for about 15 megawatts of power. So the total of that facility is a 100 megawatt data center. Anyway, project was started in March of 2020, so not too long after the last time I was here, and yes, after the start of the lockdowns in the US, and about the time I guess I started here, I don't know exactly. And it was completed on time and under budget in May of last year. And so completing a big facilities project like this on time and under budget is pretty significant. Doing it in the middle of the pandemic, which really had a lot of implications for how they got the work done, is really kind of exceptional. Let me be clear, this is not what I do. I'm not in charge of the facilities project, so I'm not bragging on myself. I'm actually saying that Anna Maria Bailey, who leads our facilities team, and her team did an outstanding job to get this all done in that basically 2-year period. So this, let's see if I can, yes, I can. Very good. All right, so this is the main area of that was developed by ECFM. These were our existing cooling towers. These are the new cooling towers, and this is the electrical yard that was all added in there by ECFM. And so here, there we go. All right, so here you see a picture of the site before the project started. These are those old cooling towers. The site was a parking lot at that point. So, this here is that there. All right. And this is our building. This is building 453. That building has a 4-story office tower on the front of the building, and in the back of the building is our compute floors. All right. And this kind of just gives you kind of a idea of the scale of what we've added in there. Anna Maria likes to say that over the time we've gone through several levels of electrical and facility infrastructure, and now she says we're up to utility grade. It's pretty impressive when you go out there and see what's there. To give you more of an idea of the scale here, this picture really kind of, I think, gives you an idea of the scale. These are people. Huh? Computers. There you go. So yeah, so I mean, it's quite a lot of, and this also continues to show the scale. This is a 30-inch pipe bringing in the cooling water from over down there, all right, and into the building, all right. And then finally, this gives you the kind of final picture of what the scale is like. This is a standard fire extinguisher. And then we have 3 of those because, as I said, we need to be able to cite El Capitan, and then we need to be able to cite the next system. So this project is designed not only to support the new system and allow us to continue running Sierra, but it's designed so that in the future, when we have El Capitan and it's getting old and along in the tooth, we're able to build in the new system, which would be ATS 6. All right, so that's the facilities work, which I think is really fascinating. When I go on tours of computer rooms and computer systems around the world, many people are surprised that I'm always like, take me to the computer room. Yeah, that's nice. Let's go look at the other stuff, because the interesting thing is if you go on many computer room tours, what you find is that the racks look a little different from one rack to the other, but they're all pretty much just racks. It's true. I mean, they look pretty much the same. We're getting this one from HPE, so we'll have a nice pretty picture on it. This is the original artist conception. It's not the picture we're actually going to have. Sorry. But it gives you the idea of what it's going to look like. But the infrastructure varies widely, and you learn a lot about how the facility actually operates by looking at that infrastructure. For El Capitan, first of all, we're confident that it will meet the stockpile stewardship simulation mission that we have for it. What we've announced is that the system will be over 2 double precision exaflops for peak capability. It's important to realize what precision it is when somebody tells you that they're building an exaflop system. So you've probably heard a lot about like this company or that company. I won't name names, but I'm sure you can fill in some, have built an AI exaflop computer. When they talk about AI exaflop computers, they're usually talking about half precision. They like to say this, but you could say, well, double precision, half precision, 16 bits, 64 bits, it's, what is it, a factor of 4? It's actually more than that because the number of transistors required to do higher precision is quadratic in the number of bits. So it's a lot more. Anyway, so just my lesson there is take everything with a grain of salt, particularly when people start talking about the performance of their systems. Make sure you pin them down as like, well, what precision are you talking about? So
precision are you talking about?
I'm talking about double precision. Although if I were talking about half precision, it would be a lot higher. Because the processors we're getting do have pretty significant capabilities in half precision. Anyway, so El Capitan we're procuring it as part of the Coral 2 procurement RFP. So in 2018, we released an RFP joint with Oak Ridge and Argonne under Coral, the collaboration of Oak Ridge, Argonne, and Livermore. And we had various requirements in there. For power in particular, we said that the systems had to be under 40 megawatts. All right, so 20 megawatts, 40 megawatts, I don't know. We're anticipating something around 30 megawatts, which is around what Frontier is. I don't remember the exact number. I think it's like 27. So Oak Ridge likes to point out that the power per high HPL exaflop for Frontier is under 20 megawatts. So I guess in some sense, they made the 20 megawatt goal. My take on it is that 20 megawatts remains an arbitrary number. It's really what you can reasonably house. And so we can go higher than 20 megawatts. What are we getting in terms of the system? It will be using the AMD processors, in particular, something called the MI300A, which is a APU or accelerated processing unit. So what does that mean? Well, you're familiar with CPUs and GPUs. An APU is a combination of the two. So it uses chiplets. So CPU chiplets and GPU chiplets. In particular, it will have what they call Zen 4 CPU chiplets. They've used a different code name elsewhere. I won't mention that since I'm not sure I'm supposed to. It would also have CDNA 3 GPU chiplets, and it'll also have HBM3 all put onto the same package. All right. We'll be using the Slingshot interconnect in a Dragonfly topology. It's basically the same network as used in Frontier. Frontier is the previous generation of AMD processor technology. They actually have discrete GPUs separate from CPUs, similar to the architecture in Summit or in Sierra. Summit was the previous Oak Ridge system. And so there's a lot of benefits we expect to get from having APUs, and I'll talk about that more shortly. A big part of these big system procurements for us is really trying to move the whole industry forward. And so we actually have two different contracts as part of the El Capitan project. A build contract that takes care of the system and some other various aspects, some early access systems that we get along the way, maintenance of the system going into the future, a bunch of different stuff. But it's really focused on what is the equipment, what is the capital equipment that we're getting. Whereas we then also have a non-recurring engineering contract, an NRE contract. And the idea is that kind of moves along what the system partner can really provide to us and everyone else. And the idea is that we get better value if we invest in their products. So we've invested in a number of things along with Oak Ridge, including the Cray programming environment, AMD's software, including their compilers, a bunch of different stuff. A big thing, though, that we're investing in is something that HPE calls a near node local storage solution, or the rabbits. And I'll tell you more about that near the end of the talk. But it's a pretty significant architectural innovation that we think is going to make the system a lot better to use and make it a lot more efficient overall. Different from Frontier, we're going to be using TOS, which I mentioned earlier is what we use on our CTSs. It's basically, well, I'll tell you more about it, but it's our software stack, whereas on Frontier, they're using HPCM and Cray OS on the compute nodes, whereas we'll be using our software. On PASI, which is very similar to Frontier, they use something called CSM, which is Cray System Management, which is yet another software stack from HPE. I won't go into all the reasons that we found that ours is better, but ours is better. I will tell you why we think ours provides better value to us. I won't tell you about the negatives of their stuff. So what is Cray really? Well, it's a full stack built on top of RHEL, or Red Hat Enterprise Linux. We add a resource manager. Historically, what we added was Slurm. If you run on big systems, most of them today, you're probably using Slurm. That was a resource manager that originally originated at Livermore. Then a couple of the people involved with developing that created a company called SkedMD and went off and worked on that. At the time that they went off and kind of productized Slurm, people who stayed at Livermore who were also working on Slurm looked at it and said, as we think about what's going to be coming along in the future, there's a bunch of things that we don't think Slurm can handle very well. All right. In particular, Slurm is very much was designed, and it's implemented, so its code is very restricted to, well, constrained by the notion of a system consisting of a bunch of nodes. At the time, it was basically all CPU nodes and connected together by a network. They're all kind of the same distance away. It's all just one big sea of nodes, and we're just going to schedule those nodes. All right. And when you change the nodes to being GPU-based nodes, it doesn't make too much difference, so that kind of still works. But as we looked at it, we were looking at things like, oh, well, you'd like to be able to say, I want to be able to schedule the amount of I/O bandwidth that this job is going to use, which is not part of running a compute nodes. Or I may have different types of compute nodes in the same system. Basically, a much richer environment and types of resources that you want to allocate to different jobs. And how are you going to handle that in code that really only is structured to handle one kind of node? So we started a project at the time that we called the Next Generation Resource Manager, or NGRM. It was a terrible name. So eventually the guys working on it looked at it and said, we need a better name. So they changed the name to Flux. Flux has been used, Flux is a hierarchical resource manager. So it allows you to like run a resource manager as a job within a resource manager, and you can do that at as many levels as you like. So that gives rise to the notions of system level flux and user level flux. System level flux actually is managing, is the resource manager for a system. And underneath that, you could run Flux to do things like I'm doing a job that is the word is slipping out of my head. An ensemble calculation. So it really consists of many different runs, maybe of the same application, maybe of different applications. And currently, how do we run that on something that's like a Slurm-based system? Either I submit a whole bunch of little jobs that are kind of disconnected from Slurm's viewpoint, and you can add dependencies to them so that they'll run in the correct order, but they're not guaranteed to keep getting the same allocation. Or you can get one big allocation and then try and implement your own resource manager inside of that. All right. And it's kind of, so a lot of people running ensemble calculations end up spending a lot of time kind of reinventing the wheel by re-implementing a resource manager. Flux allows you to run Flux on your allocation and then just allocate your resources from Flux. And as the application programmer, you no longer have to think about how am I going to handle that. I just submit the jobs to my Flux instance, and I don't overwhelm the system level resource manager. So it has a lot of benefits. I mentioned the rabbits. Those are actually essentially a different node type, and I will explain that later. But that became a reason why Slurm really wasn't going to cut it for us on El Capitan. So we'll be running Flux on El Capitan. We're also starting to run it on our CTS2s. So that's where that stands. We also add Luster, which is a parallel file system. On top of TOS, we run something we call TCE, which is a TriLab compute environment. And that really adds kind of all the user-facing software, the compilers, the runtime libraries, the tools such as debuggers, and performance analysis tools, whole host of things like that. TOS actually includes some of that stuff, but it really includes a very limited set of them. Kind of like this is the base compiler that you can use it. And it turns out that users, if you've talked to 10 users, they want 10 different compilers. Some of them maybe 15 different compilers. I don't know. I kind of already said some of this. TOS is a common operating system that we use on all of our Linux systems. So going into the future, all of our systems, it's really just a software stack for HPC clusters, but it's also a way for us to build and provide quality assurance and configuration management for our systems. All right, so we have a pretty large build farm that has a wide range of different node types and regularly run CI/CD for TOS on that build farm. So we make sure that it stays running correctly on a range of different system types. The reason we do this is that now, I mentioned we have 40 different clusters, over 40 different clusters. So we have a lot of systems, right? And what that ends up meaning is we want the sysadmins and the operations team to be able to handle a number of different systems. And while the hardware may vary, being able to go on and say, this is what the system software looks like provides us significant benefits in terms of total cost of ownership. It makes it just a lot simpler for one team to operate this wide range of systems. And it's actually used on all of the CTS systems in the TriLabs. So I've already covered most of this. People ask, why do you use Red Hat? Well, we use Red Hat because they have by far and away industry-leading quality assurance testing and support. We have a very close relationship with Red Hat. We have one of their people on site at Livermore. One of our people, kind of the main lead for TOS is I forget the exact term, but he's like a Red Hat certified engineer or something like that. But what that means is he actually ends up having access to the Red Hat internal repos. If there's a report of a security problem before it's made public, he's aware of it. He's already then able to go and make sure that the fixes are going to work with TOS, and basically we get 0-day support for security issues, which is a big deal to us. Should be to everybody. These big systems are definitely targets for people who want to do things they shouldn't do. Anyway, so it provides us, a way of being certain that the system's running the way we want it to, and not running things we don't want it to run. This shows you kind of a list of different things that are included in TOS. A number of these things were actually developed at Livermore, like PDish. I think Munge was also. I already mentioned that Flux and Slurm were. LVMS is a monitoring software that was developed at Sandia, but there's a lot of effort over time, but really everything in here is open source and widely available. So what exactly really is TOS? So I said it's we use RHEL, and have to say that with a little bit of a caveat. So RHEL has about 40,000 packages. All right, we go in and down select to about 4,300 of those packages. The idea being that, in order to reduce system noise, you don't want to run everything under the sun that you could run in the OS. So we really cut down to what we think is essential. Of those 4,345 packages, we patch and repackage 37 of them. So we're making very few changes to the standard RHEL distro, other than down selecting from the large set of things we could use. We add only 253 packages that add HPC functionality that we've not been able to upstream into RHEL, and so we end up with 4,600 packages. And I should say that 253 packages, that may sound like a lot, but it's really not. When we started this, we were up in, I don't know, like 1,500 packages. We've worked very hard to get everything that we do upstreamed. Some of this stuff, the RHEL is just like, yeah, nobody wants that, except that we do, and we think other sites do. So it turns out that pretty frequently, for instance, you end up with very long path names on supercomputers. All right, I won't go into why, but you do. So where are we? So I mentioned we're actually already starting to take delivery of some equipment from El Capitan. We've got all the infrastructure racks. The file system has been delivered, and we're in the process of bringing this up. The 300A, we don't have any of those on site yet, but they do have them at AMD Austin. I've been there. I've seen this. These are AMD. Well, they're 300A systems using AMD reference boards. So those are single socket boards. And the ones on this side are so they're the actual HPE pilot blades. So the early versions of the blade that HPE is developing. And so that's 2 quad socket compute node boards. So you get 4 of these APUs, and 2 of those nodes. You get 4 slingshot NICs per node. They're wired up so that each APU basically has preferential access to one of the NICs. What you don't see here that you would see on a Frontier node or Pawsey node is a separate CPU. You also don't see, because of the cold plates, but you wouldn't even if they weren't there, any DIMMs. So there's all the memory is in the HBM3 stacks on the APUs. And that makes for a big difference because now if you've worked on any of the GPU-based systems, you know that what you end up having to do is a lot of work to stage memory data back and forth between where the CPU has good access to it and where the GPU has good access to it. And you work hard to make it so that you move it over, leave it there for the GPU to access and only move a little bit back, but you're still working hard to figure out how to do that. Whereas with this system, since all of the memory all of the processors have equal access to all of the memory, we expect it to be a lot easier for our application teams to use. All right. So it really is a unified on-package pool of memory. It's different from what on other systems you hear talked about as unified shared memory, where you can address memory on either memory pools, but they're really different memory pools with different access characteristics, different performance characteristics. There will be 24 of the Zen 4 cores, a whole lot of GPU compute that I'm not going to talk about more than that. Overall, on the package, you end up with 146 billion transistors, so that's a lot of transistors. 128 gigabytes of HBM3 per APU. All right, so each node will have 512 gigabytes of HBM3. So a big thing is because now you don't have to go copy data back and forth. We expect this system to be significantly more power efficient than Frontier or other GPU-based systems. How much remains to be seen, but I do expect El Capitan or its TDS to end up being #1 on the Green 500. So I mentioned already that it'll be using the 5-nanometer process technology with what they call 3D stacking. Here's kind of a little cartoon of the organization of it. Get CPU chiplets, GPU chiplets. AMD claims that we would get 8x higher AI performance and 5x higher AI performance per watt. That's probably half precision, or it's half precision with single precision accumulates, but basically we expect that to translate pretty directly in a comparison of the MI300A to the 250X. All right. I've talked about this already, so I'll skip it in the interest of time. What are the rabbits? So the rabbits are a near node local storage solution. The idea is that basically they enable us to reduce system interference by moving I/O off of the kind of critical path and out of the network. And to show you what I mean by a near node local storage solution, I'll just show you this. This is essentially a Frontier node. It's actually what we have in our early access system 3s. So we actually have rabbits deployed. Early access system 3s are systems that, as I said, they have similar nodes to Frontier and the Pawsey GPU nodes, 4 MI250Xs, Trento's CPU. We have ones with 24 nodes, 32 nodes, and 38 nodes. The one with 38 nodes is something just slightly higher than number 100 on the top 500. The one that's number 24 is in the like 170s, 160s. So they're pretty powerful nodes. You should realize that, like 24 nodes inside the top 200 is pretty amazing in my opinion. Other systems of that size have a lot more nodes. But anyhow, so what the Rabbit is 2 separate boards. It's a processor board that has an AMD EPYC processor. I think they call it a Rome processor. 2 slingshot NICs that can connect it to the same high-speed network that the compute nodes are attached to. And then but that it also connects over PCIe into the Rabbit storage board, or the Rabbit S, that has two PCIe switches that it connects into, and also off of those PCIe switches are 18 SSDs, so non-volatile memory that we can access. But in addition, the compute nodes are able to use PCIe to connect into that PCIe network as well. So what that means is that you can directly access these SSDs from the compute nodes. The way it's laid out is you get the compute nodes in a chassis, so you get 8 compute blades, so 16 nodes that can then be associated with one Rabbit module. So the HPE racks are such that they're very large racks. They're more than twice the size of a standard 19-inch rack. On the front of them is where you put all these compute chassis. So you get 8 compute chassis in a rack. On the back side, you get a place for your switches, for your first level switches. All right, and you can have essentially 4 switches for every compute chassis, 4 switch blades. All right. Well, that's a lot more network than we thought we needed, and even HPE thought or Cray, back when we first set up the contract, thought we really needed. So that actually left 3 of those 4 spots for switch blades open. And so instead of leaving them empty as they did in Frontier, we decided we wanted to put these Rabbit modules in there. All right. So that's kind of a mock-up of it, what it looks like. So you end up with the front of it gives you access to the SSDs, so you can replace them pretty easily without having to take apart the whole module. The big thing is the software that you actually run on it. And so the software allows us to run it in a couple different modes. So first of all, you can you basically allocate stripes of those SSDs across, so a stripe of capacity in all of the SSDs. We can fit, divide it into some number of stripes, probably 32 is what we're looking at. And then you can allocate those to different jobs. And so you can take a stripe and allocate it as a block device to one of those compute nodes. And then it appears just exactly as local storage available to that compute node that also happens to be accessible from the Rabbit P. All right. And there's a long story about, well, what file system allows you to have 2 images mounting that at the same time. I'm going to answer questions about that later, but I won't go into it now. But the main thing is that then says, all right, I can write a local file from my compute node and then have the Rabbit P drain it off to my parallel file system kind of at its leisure. So it's taken the storage, it stores locally on the critical path for my application, and then I can, using lower network priority, actually move that to where it can live permanently. In addition, we can also create what we call transient luster file systems on the Rabbits. So we can take a bunch of stripes really anywhere in the machine and use those to build a luster file system that we use for a specific job. Why would I want to do that? So the bandwidth to the storage scales with the number of compute nodes under that, essentially, all right, or the number of compute nodes in the system. So we can afford a lot more bandwidth to the Rabbits than we can to our parallel file system. It'll be roughly 10x. All right. And so that way you can much more quickly store shared files to a transient luster file system, and then again move it off to the parallel file, to the permanent luster file system in our capacity tier, kind of at lower network priority and outside of the critical application path. The final thing that's important to realize is that those Rabbit Ps are using a general purpose CPU. You can run really pretty much anything on there. We can run user jobs on there in containers if we want, giving us some isolation from different jobs running on the same Rabbit P. And so in effect, we can do things like run something that, as the data is stored locally, goes and examines that data, does some analysis of the data, maybe allows the application programmer, the application user to steer their simulation, hopefully can allow them to do things like data reduction. So knowing that this data is what I really need to store, so moving less data over the permanent file system. Anyhow, so for me, I actually view the rabbits as essentially data analysis nodes. So they're really a different node type. And so this goes back to what I said earlier about we need flux in order to be able to schedule data analysis nodes with compute nodes in the same job. We also need it to be able to schedule those stripes of the storage resource. We have a much richer resource set in El Capitan than what we've traditionally been scheduling. All right, so I'll try and finish up somewhat quickly. So what are the shortcomings of current approaches in terms of energy efficiency? So a big shortcoming is that I've mentioned how we can basically move a lot of the IO traffic off of the network with the rabbits. Well, using HPL to measure the energy efficiency of El Capitan, we will not see any benefits from the rabbits because HPL does no file IO. All right. Even if we think of it in terms of the energy efficiency of real applications, and we measure it in gigaflops per watt. Okay, we measure how many gigaflops it does and what the time to solution is, and then divide by energy to solution. It'll sort of appear there, but it's very nebulous in that. So I think we need to rethink what we use, how we measure energy efficiency of these systems. A little bit more on this. So when we think about energy efficiency, what we really are talking about is that there's this Pareto front. We have the time to solution and the energy to solution. And there are going to be solutions which I can't finish any faster without taking more energy. All right. But there also be ones where, well, I could finish just as fast with using less energy. All right. And so it creates a Pareto front. And a lot of the work that we've done over time has been looking at how can we ensure that we run on this Pareto front. All right. So this goes back to the questions of, well, what motivates users? Well, most users, what they care about is getting their job done as fast as possible. And they're not really worried about how much energy it uses. So this point, from the standpoint of when we think about energy efficiency in terms of this Pareto front, is just as good as this point, but it uses a lot more energy. All right. Nonetheless, we can think about doing things like charging users for kilowatt hours instead of node hours, right? Which would then mean maybe we're motivating them. They still want to get their work done fast, but they don't want it to cost too much. So maybe they move back along this curve. But now what we've really done is move users from one of these dominated points to somewhere on this curve. So they're using less energy to get their work done, but they're often frequently getting their work done faster. All right, that's often the most energy efficient solution is often the fastest solution. All right, so what does that end up meaning? Well, it ends up meaning that you run more jobs in the same overall, because like we don't leave the system sit there idle, and if we left it sit there idle, then it would be using power to do nothing, and that's not really very efficient. All right, so what ends up ultimately happening is if you run your system really with significant energy efficiency, you end up consuming more energy than you would if you ran it not efficient. I know that sounds strange, but it's actually the result, because you tend to drive up your power requirements to drive down your time, and that means that you've gotten, I know it's backwards, but it's actually the reality. That's what the math says. And so frequently the total energy use of an energy efficient system will be higher than of an energy inefficient system. So that's good. We're getting more work done, and we really buy the systems to get the work done. And if we're paying a high power bill, we want it to be justified because we're getting a lot of useful work done, not because we buy the computer to get the work done, not use energy. Don't buy the computer, we don't use any energy. Yeah. But anyhow, so the conclusion though out of that is that focusing just on energy efficiency does not actually address the concerns that cause people to ask us how energy efficient is your system in the first place. All right. And so largely, I think we really need to be more concerned about where we're getting the power from than and not focus so much on how we're using it. Not to say that how we're using it isn't important, but that where we're getting it from is what we have to focus on in order to respond to the concerns that cause people to ask us the question. Anyway, so that's pretty much it. I will point out, I kind of mentioned this, Frontier achieves 52 and change gigaflops per watt. So yes, they are less than 20 megawatts per HPL exaflop. So that was a pretty significant achievement. I expect, as I mentioned, El Capitan will be more efficient. I've talked about everything else on here, and I'm happy to answer questions.